Hello. Let's take a look at the cumulative spectrum and see if we can understand how it's computed and what it might be used for, and compare it a little bit to the regular spectrum. Here's the D3 key on my Kanabi, and here is the spectrum plotted three ways. Up here it's plotted logarithmically on the power, logarithmically, or in decibels, and it's plotted linearly in frequency. Over here, linear frequency, dB power. And I like this approach because it shows when the partials are equally spaced. Here, for example, is the first partial at 147, second partial at 293, so forth. You can also get an idea about inharmonicity if you also plot the location of the harmonics. So it's handy. Here's some splitting, for example. It will be brought out when you use this kind of plotting. The lower power components, for example, here's one that's 36 dB down at 1600 or so, and it shows it's there even though it's quite weak. Here's another way of plotting it, sometimes used. Linear power, not logarithmic, but linear, and then linear frequency. And so here we have the same information, 147, 293, so forth. But you can see that some of the low frequencies here, they don't come out very well, and some of the granularity you don't see at all. Third way of plotting it uses logarithmic power, or decibels, and logarithmic frequency. And this is often used by electrical engineers, especially when they use harmonic analyzers or special hardware, because that's the way the graphs sometimes appear on the little CRT. You can see here, same information. Here's the first partial, 147. Second partial, 293, corresponds to that guy and that guy. And so the frequencies, the components kind of get squeezed together as frequency increases. Now here's the cumulative line spectrum, and it will come from this particular way of plotting, this middle one. And you do it, and you calculate it by starting out at zero frequency, and you move along with increasing frequency, and as you move along, you add up the power at each frequency. You accumulate it. So here, for example, I'm going to accumulate a lot. Then for a while, I'm not going to accumulate much at all. Over here, start out, zero frequency, start moving along. And you can see there's not much accumulated. And then here it is at 143, we get a jump because we're accumulating the power in that peak. Then we move along and not much is accumulated. And then here we get a power from this peak. Now it's interesting that this is 29% here, and this is about 31 here. So even though this peak is a lot higher than this peak, the power amount in terms of accumulation is about the same, because the cumulative line spectrum takes into account the width as well as the height of the peak. And then we move along to more, and we hit this third peak, and we see a jump, and then so forth. And you can see over here, now we're seeing the influence of the weaker components, and we get not much contribution in percentage. And then here's a relatively large jump as a consequence of this component right here. So I'm plotting accumulated power in percent versus frequency. And this graph will always end up at 100% when you get to when you cover all the frequencies. Okay, just what I said a minute ago. Move along the frequency axis and add up the power as you go. And it is sensitive to peak height, but is also sensitive to the width. So sometimes these jumps are not what you'd expect by looking at the peaks here because of the width. And of course it has the same information as this graph or this graph or this graph, just presented in a different way. Okay, time for a movie to try to illustrate this one more time. Okay, I've got the frequency, the spectrum over here, and I've got the cumulative spectrum down here. I'm going to start here at 0 frequency and move along the frequency axis, and as I do, I'm going to accumulate the power and plot it down here. Okay, let's let her rip. Move it along, no accumulation. Whoop, there's a accumulation. Spike, accumulation, so forth. Every time I see a spike, I jump in the cumulative spectrum. Not much here because these are weak spikes, or narrow and weak. Coming along here, there's one that's got some power behind it. And then it's going to end up at 100%. Okay, hopefully at this point you have a feel for how the cumulative line spectrum is computed and what it means. Now let's look at an example of before and after voicing, and we'll pick F5 sharp. Okay, here's the spectrum of F5 sharp before voicing. Here's the same thing after voicing. And what do you see? Well, you see that before you had a lot of power, the second harmonic, in fact the second harmonic, or the second partial, was the strongest component, at least peak-wise. Then you have a drop-off. Down here, after voicing, you have almost all your power in the first partial, and then this thing is what? It's 22 dB down. And then this third partial is 34 dB down. So the voicing has taken the power out of the higher partials. The cumulative line spectrum is the same, shows the same information. The blue is before, comes up here, and it shows it's got some power at the first partial, but not much. Well, not much, about 30-something%. Well, actually, is it 30? Yeah, about that. Almost 40, actually. And then it comes across, and then we get another jump over here. We have, well, let's go back. You have a contribution of about from 10 up to 50 or so. So about 40% contribution here from the first partial, and about, let's see, this is 60 up to, 30+% contribution from the second, and then some from the third partial. After voicing, you have percentage-wise a little bit more power down below the first partial over here, but you can see almost all of it is at the first partial, and there's a little bitty hump here, but not much, and then virtually nothing at the third. So this particular thing, this particular way of plotting can be helpful sometimes if you want to overplot. For example, if I were to compare these two spectra by overplotting, in other words, plotting these two spectra on the same graph, it wouldn't be particularly insightful because these things are so noisy and it's difficult to gain the insight. And they're messy. These are smooth curves, they're easier to interpret. So there are some advantages, and it all depends on what kind of insight you're looking for. Which again is the goal. The goal is insight. So, thanks for watching and listening.